Okay, welcome back. Happy Monday. Today is kind of or this week is kind of a funny week, so let's talk about it. Today is an ordinary Monday. This coming Wednesday, GCC treats like a Friday. I'll say that again. This coming Wednesday, you go to your Friday classes. That has no impact on us because we meet on both Wednesday and Friday, so we will see each other Wednesday coming up. But if your Wednesday, Friday schedules are different, then you got to pay attention, okay? So you're going to your Friday classes on Wednesday. Evening, Wednesday is Wednesday. Do you have a Wednesday night class? Go to your Wednesday night class, right? So Friday during the day is a Wednesday. Questions on that? The reason Friday during the day is a Wednesday is what is this coming Friday? It's Veterans Day, and we do not have any classes on this coming Friday. And so just to try to balance the scales, we lost a Friday. We're going to give it to you on Wednesday instead. All right, so that's the plan for this week. Today we're going to cover something called dividing polynomials and the factor theorem. Don't forget that project number 3 is due 1 week from today, Monday coming up. Any questions on the calendar? Have folks started on the project? Yeah? Looked at it? You have a copy of the project. That's all you're willing to commit to. All right, let's jump in here. So normally we don't do the preview exercises together. We just jump in on the demo part, but like I said, some of us have had too long between now and the last time we did long division. So we got to refresh our memories because long division with numbers is a whole heck of a lot easier than long division with x's, and that's the goal for today. So let's remind ourselves of how to do the number long division. First thing, 11 goes into 78 how many times? 7 times. So I put a 7 right up there, and then we multiply that 7 times that 11. 77 goes there, and then we subtract. We're left with a 1, and then the other 7 in this original number now comes straight down, and then we repeat. 11 goes into the newest thing. That's the whole process. 11 into the new thing. So 11 goes into 17 just once. 1 times that 11 is 11. Subtract, and we get 6. Now, depending on what you're doing, some of you might have done, oh, okay, what comes after? 0. Right, you might have brought like a 0 down here, and that's okay, and you can get a decimal expansion. That's actually not what we're after today, so we're not going to bring the 0 down. Instead, we're going to stop right there and say 6 is called the remainder. Remainder 6. Remember this? Remainder is 6. And the reason we know we're supposed to stop there is because it says write your answer as a quotient plus a remainder over the divisor. So here it is, 787 divided by 11. How many times did it go in? How many like whole number times? It went in 71 times. And then there was a remainder of 6, but it's not just 6, it's 6 what? 6 11ths, right? 71 plus 6 11ths. And normally you wouldn't even write the plus sign. 71 and 6 11ths, right? But when there's x's in here in a minute, we're going to have to write the plus signs. Okay, so that's one way to think about the answer to this question. There's another way which wasn't requested here, but would you agree with this? If I do 11 times 71, that's going to get me pretty close to 787, right? Now don't do this on the calculator. This is really more of a thought thing. 11 times 71. It's not equal to 787, but it's close. How do I balance the scales so that it actually is equal? Plus, how much? 6. That's going to make it equal. That's it, right? You buy that? Might not be the way you, I mean, I'm sure we're comfortable with the thing I wrote in black. Like that's something you've done before. But the thing in orange might not be as familiar to us, but it's equivalent. One way you can see it, even without like thinking about why it makes sense, is if I multiply everything here by 11, yes? What happens on the left-hand side? Cancel, we get 787. 11 times 71 is what I've written here. And what happens when you do 11 times this fraction? When it cancels the 11, we just get 6. So they're equivalent, right? They're equivalent. Yeah, but even without thinking about that like the algebraic way, it's just like, hey, you know, like 11 goes into 787 71 times, meaning if you do 11 times 71, you're really close to getting the answer of 787. How close are you? You're off by 6. That's the remainder. We didn't quite get there, okay? All right, so this second way is going to be useful for us later today. All right, I think that that is good. Let's skip the rest of that and jump to the next page. Okay, take a look at this division problem right here. How much is the divisor, which is this guy in the front? That's 11. How much is the dividend, which is the guy in the 787? So this is exactly the same problem, but now we're just writing things out in terms of like powers of 10. And it turns out to be quite useful for us for where we're headed. So let's do this. In this case, I'm not seeing 11, I'm seeing 10 plus 1. And so I'm going to take that 10 and put it into what number over there? 700. How many times does 10 go into 700? 7? 70 times, right? 10 goes into 700 70 times. Put a 70 right up there. And then what do we multiply? What times what? 70 times the 10 plus the 1, right? That 70 needs to multiply by this entire thing. I mean, I know it's 11, but I got to do 70 times whatever is out here. So 70 times 10, that's 700, plus 70 times 1, that's 70. Everybody buy it? We're still doing thing on top times everything in the front. It's just a distributing way of looking at it. Okay, and what's the next step now? I'm not ready to bring down yet. What do I do with these two things? Subtract them, right? So 700, 700. What happens when I subtract? They cancel. That was the whole point. If they didn't cancel, it means you put the wrong thing up on top, right? Like you put 70 up there because that's the thing that made them cancel. But then we do 80 minus the 70 and we get 10. Okay, and now what comes down? Plus 7. And I know it's 17, and 17 I think is, was part of what we wrote on the previous process. So it's just another way of saying exactly the same stuff that we did. Okay, and now we're going to do another division. What into what? 10 into 10, right? Notice that plus 1 didn't make any difference, right? Like how many times 10 goes into 700? It's pretty much how many times 11 goes into 700. Like it hardly makes a difference. The most important thing is that first thing, the 10. It's the biggest thing. Okay, so let's do 10 into 10 goes how many times? Plus 1 time. And then what gets multiplied now? That 1 times the 10 plus 1. So 1 times 10, and then 1 times 1. And then we subtract. And what happens with the 10s? They cancel. Again, if they didn't cancel, it's because we messed up. And then the 7, subtract 1, 6. That 6 looks familiar. That's still the remainder. The number on the top is still what? 71. Same answer, right? We got 71 before, 71, remainder 6. Exactly the same thing. But this is going to help us over here with another version of that kind of problem. What we're going to do is let x equal 10. And we're going to rewrite that original problem over here with x's. So instead of 10 plus 1, we're just going to put x plus 1. Everybody put an x plus 1 out there. Everybody see it? Just change the x into 10. All right, let's work from the right side. I see a plus 7. I'm just going to put the plus 7 there. Next thing I see is an 80. That's really what in terms of x? That's 8x, right? 8 tens. So 8x can go right there. 700, how am I going to build that from x? You could do 70x. We're not going to do that. Any other thoughts? 7x squared, that's what we're going to do. Does it work? How much is x squared? 100. 700s. That's a very natural way to write it, right? 70 times x, perfectly valid. But really what we want is x squared, and if we had thousands, we would do x cubed, right? Okay, so we are going to do this division problem. It's going to look an awful lot like the first division problem we did. Let's give it a shot. Before we did 10 into 700, right? We ignored the plus 1, and we ignored the 80 and the 7. What into what here? X into 7x squared, ignoring everything else, right? X into 7x squared. Now, some of us are going to be able to do that without really even thinking about it. X into 7x squared. But a lot of us are going to need to think about, like, what does that really mean when we do x into 7x squared? What it really means is this, x into 7x squared, right? How many times does x go into 7x squared? I'm asking that like the answer is a number, but the answer is not just a number. The answer has x in it. What do you get when you reduce this fraction? 7x. That's how many times x goes into 7x squared. It goes in 7x times. So that 7x is our first answer. Put it right on top of the 8x. I mean, you can put it anywhere you want, but I like to line up the powers on x. That's one of the trickier steps. Questions? Ask now. I'm not sure where that 7x came from. Okay. Next up, we did 70 times 10 plus 1. Now, 7x times x plus 1. That's what we're doing. And we are distributing that 7x through. So what do we get? 7x times that x, 7x squared, plus 7x times that 1, 7x. And then a big old horizontal line. And what are we doing? Subtracting. And over here, what happens with the 7x squareds? They cancel. And if you didn't do it right, it wouldn't have canceled. If you put anything over there on top except 7x, you'd have x squareds left over. And that's a big warning flag. Hey, this did not work. Go back. Okay, so the x squareds cancel. 8x and 7x is 15x. Is that right? It's 1x. What are we doing with those two things? Subtracting those two things. And so for me, because it's so easy to make this mistake here, I typically do this. I'm not requiring it from you, but this is what I'm imagining. It's minus all of it. Okay, and now yes, still the 7x squareds cancel. That's 8x minus 7x gives me just a single x. Coming back over here, after we got the 10, what did we do? We brought down the plus 7. What are we going to do here? We're going to bring down that plus 7. Do I see it? Okay. Coming back to the original numerical example, we did 10 into 10. X into x, right? It's always this first guy into whatever you get. So how many times does x go into x? It goes in once, but I like writing this over here for folks who just sort of need a little bit of a push. That x going into the thing that we just got out. Okay, yeah, it's just 1. So that 1 goes right up here, plus 1. Again, I like to line up so that goes above the plus 7. Multiply what by what? That 1 times the x plus 1, not just the x, but the whole thing over there. So 1 times x plus 1 is x plus 1. 2x plus 8. Oh, I did it again. Just not having a good day. Subtract. What do we get? 6. 6 is good. Okay, if there were anything else to bring down, we would. But we've run out of terms and there's no like put a decimal point and then a lot of zeros. You just stop when you run out of terms. So we're done. Now it's just a matter of writing our answer. We're going to write it in 2 ways, both ways that we wrote it on the previous page. On the one hand, if I take, I'm not sure where to put it, I'll put it here. If I take 7x squared plus 8x plus 7, and I divide it by which, what are we dividing by? X plus 1, that's the thing out front, that's what we were divided by. When we do that division, what do we get? 7x plus 1, that was the quotient. That's what we got. It didn't go in evenly, but that's like the whole number part. That's like how many times x plus 1 went in to the thing on top. Plus, what was the remainder? 6. but it's not just a plain old 6. It's 6 out of something. 6 out of what? X plus 1. It's 6 out of that guy in the front. The reason we did the numerical example on the previous page was to remind you that this made sense with numbers. The pieces go in exactly the same places when there's variables. 6 out of whatever was in the front. I think it was 11 on the previous page, right? 6 out of 11. Now it's 6 out of X plus 1. Okay, that's good. Yeah, and then another way to say exactly the same thing is to say that if you wanted to multiply the original X plus 1 by the 7X plus 1, it will almost give you the entire original thing, 7x squared plus 8x plus 7. I'm putting equals. It is not a true equals right now, but it's almost there. How far off was it from being the entire thing? It was only 6 off from being the entire thing. Just 6. The x plus 1 goes away. Again, you could imagine multiplying both sides by x plus 1. Like if you just want to think about it algebraically, that's how you do it. Distribute that x plus 1 through everything. And the cool thing about writing it in the last way that we wrote it here is that this is actually something we can check, right? Even if you don't buy any of the stuff that we just did on the board, this is something that you can check. It's either true or false. And if it's true, that means that we must have done the division right. And so let's try it real quick. If we FOIL, what do we get for firsts? 7x squared, that agrees. What do we get for outers? 1x plus inners, 7x altogether, 8x, that agrees. What do we get for the lasts? 1, right? Plus 1, that doesn't agree. Plus the 6, that was the part that we needed to add in there. So it worked. Okay, so that is polynomial long division. Let's go to the next page. So we're going to try another problem. We're going to do this one quicker than the first one. It's exactly the same process. Let's give it a shot. It says divide 6x squared plus 5x minus 6 by 2x plus 3. First thing you need to know is what goes where? What goes out in front? It's the 2x plus 3. I mean, it's really easy to get these guys swapped. You got to make sure you put the right thing in the front. And then all of the other stuff goes inside here. 6x squared plus 5x minus 6. Okay, first step is the hardest for a lot of folks. What into what? Yes, first into the first. That's a great way to think of it. 2x into 6x squared. 2x into 6x squared. There's only one right answer, but if you need help, you just 2x into 6x squared. How many times does it go in? 3x. 3x is good. Again, line it right up above the x term in the original. So lining it up is just an aesthetic thing. Like, don't worry about putting it in the wrong spot later on. It's just a detail. Okay, now we're multiplying what by what? 3x times the 2x plus 3, the whole thing. So we distribute 6x squared plus, try again, 9x there. What happens with the 6x squareds? Cancel, that was the goal. What about the 5x and the 9x? Negative 4x. Nobody wants to say 14x? Not 14x. No. Okay, and then what comes down? The minus 6. And then we repeat that whole exact process. Still 2x, but now into the new thing. 2x into negative 4x. 2x into negative 4x. How many times does it go in? Negative 2 times. Negative 2 times. Okay, and now we're distributing that -2 times the whole 2x plus 3. I see -4x minus 6, is that right? Okay, what happens when we subtract? 0, not -12, 0. Getting 0 is not why the process just stops right there. Why did the process stop right there? How do we know we're done? It's not the 0. There's no more terms. That's what makes it stop. You could get 0 like in the middle of the process and still have to bring down the next term. Okay, so it just happens that 0 coincided with the end, but really there's nothing left to bring down. Okay, so then I think we are good to go. It's just a matter of writing our answer. Have to write it in 2 different ways. Take the original thing, 6x squared plus 5x minus 6, divide it by 2x plus 3, put an equal sign, and then fill in the blank over there. I want you to write the 0, even though you don't need to write the 0. I want you to get in the habit of putting the remainder over the divisor. So I want to know what the answer is. How many times did it go in? 3x minus 2 is good. Typically, though, it doesn't perfectly go in. Doesn't go in evenly. So there's always a plus. 0 is the remainder over 2x plus 3. That's where the pieces go. Everybody see it? Again, we didn't need it in this one only because it was a 0. But normally you need it. And the pieces always go in the same spots. And that means that we could write the other version of that equation. So again, imagine multiplying everything by 2x plus 3. It's going to get rid of all your denominators. So what happens on the left-hand side? What do we get? That's good there. Equals. Now 3x minus 2. What comes next? Multiplying everything by 2x plus 3. So that guy actually still has the 2x plus 3. Plus 0, and then that denominator disappears. There you go. Okay, 2 ways to say the same thing. So every division problem, you should be able to write those 2 different ways to say the answer. Okay, let's get some vocabulary here. I've been using some of these words already. The 0 is called the remainder, right? So in our case, the remainder here was 0. The remainder on the last problem was 6. But it's quite possible that the remainder is going to have x's in it. Maybe the remainder is x minus 3. We'll see some of those. So I'm trying to generalize here and say I'm not just going to call it r for a number, but I'm going to call it r of x. Remainder potentially is going to have x's in it. What was the 2x plus 3 called? Remember this division word? 2x plus 3 is not the quotient, it's the divisor. So let's call this guy d of x for divisor. I'll get that plus sign in there. We created the 3x minus 2. That was like our basic answer to this division problem. What is that guy called? That's the quotient. That's how many times the thing goes in. So what this says is that the quotient gets multiplied by the divisor. And then the most neglected division word is this, the name for this guy. That's the dividend. Dividend. All right, unfortunately, I can't call it d of x because d of x stands for our divisor formula. Your book calls this guy f of x. I'll just write the word dividend here. The thing you're dividing into. Yeah. So if you look at the original problem, this guy right here is the dividend. And this was the divisor. And we created 2 answers. We created the quotient, which was the thing on top, and then the remainder, which was the final piece. Okay, so what this says in general is that, hey, the dividend is always equal to the quotient times the divisor plus some remainder. And that thing has a name. It's called the division algorithm. It's important enough to have a name. And that's the equation that we just wrote there, okay? It says, hey, you want to do some division? No problem. You're going to get a quotient, which will probably have x's in it. And you're going to get a remainder, which will probably have x's in it. And that's the equation that all of these x's will satisfy. Okay, let's go on to the next page. And we've got one more theorem that we're going to build today. This one's going to go pretty quick. It's an important one, but it's easy to get mixed up on it. So let's make sure we get this solid here. Suppose that the polynomial f has zeros at x equals -2 and 1 and 3, all with multiplicities of 1. What are the factors of the function f, and what do we know about the value of a? So let's try this. Let's start on the far right. X equals 3. You can see the x-intercept right there. The only way that x equals 3 is going to be a 0 of this original problem is if what is a factor? It's x minus 3. You buy it? I'm going to squeeze that in. There's not a lot of room. Because regardless of whatever else we fill in the blanks with, and regardless of the value of a, if you find f of 3 right now, you're going to get a times 3 minus something times 3 minus something times 0. Yes? 3 minus 3. And what is that equal to? It's equal to 0. Okay. And so because we know we're supposed to get 0 at the end, when we plug 3 in, you got to have an x minus 3 appearing someplace. Same idea for this x equals 1. That turns into x minus 1, right? It's the only way that x equals 1 is going to give you a 0 in that function. -2? Yeah, I'm going to write x minus -2. You can write it as x plus 2. Okay, there's this question here about what do we know about the value of a. This is just a remind you question about end behavior. You guys remember whether a is positive or negative dictates which direction, left or right? Yeah, it dictates to the right. So in this case, you can see to the far right, we're going up to positive infinity. So what kind of a number is a? Is positive. That's what we know. So that's just kind of a reminder. Okay, so let's start filling in some of the blanks here. We're going to fill in the blanks, the vice versa part first. We were given that x equals 3 was a 0, meaning f of 3 was supposed to be 0. So right away that told us what was a factor? X minus 3. Got to be. The only way f of 3 is equal to 0 is if x minus 3 is one of our factors. Fill in the other two blanks right down there. Okay, so that's the direction that we just used. Again, you could put x plus 2 if you want. But then the other direction is true as well. If blank is a factor, then f of blank equals 0. Let's start with the x minus 3. If x minus 3 is a factor, then what value of x definitely makes the function 0? It's 3. And it's just the same thing, but going the other direction. Go ahead and fill in the other two blanks there as well. Okay, so x minus 1 meant f of 1 equals 0, and x minus -2 meant f of -2 is equal to 0. Okay. All right, so what we just sort of established here, again, is important enough to give a name to. It's called the factor theorem. It's got two pieces, starting with a polynomial f of x. If f of c is equal to 0, then x minus c is a factor of the original f of x function. Right? If f of c is 0, then x minus c is a factor. It's just what we saw there. And then the other direction. If x minus c is a factor, then for sure f of c has to equal 0. Okay? Okay, so now we're going to answer some hard questions using this factor theorem. Number 5. Let's just focus, forget the question itself. Let's just look at this equation. What we're after is the solutions to that equation. How many solutions are we expecting? 3, for sure, right? Whatever that highest power is, the degree is 3. That's how many solutions we're going to get. If that were a quadratic equation, x squared is the highest factor, or highest power, and you could use the quadratic formula to solve the equation, right? If it was just an x squared equation, you could use the quadratic formula. But this is an x cubed equation, and I'm guessing that none of us knows the cubic formula. There's one. Just like there's a quadratic formula, negative b plus or minus, there is a even more complicated cubic formula. We don't know it, so we can't use it. So we need something else. The something else that we need is a way to open the door here. And if we just read right after that highlighted thing, given that negative 2 is a 0 of that function, we're given that negative 2 is a 0 of that function. Okay, well, first of all, let's see if we believe that. F of negative 2, let's find it. Formula is given here on the left. So 2 times negative 2 cubed, right? See what we're doing? Minus 3 times negative 2 squared, minus 11 times negative 2 plus 6. Just plugging negative 2 in, no calculators here. This is 2 times how much? Negative 8 minus 3 times 4. Let's do this multiplication here. That's a plus 22 and plus 6. All right, so that's equal to negative 16 minus 12 plus, we'll smush these together, 28. What is it equal to? 0. Oh, good. That's what they said. They said negative 2 was a 0. So we confirmed. So again, thinking back to the original problem, which was to solve that yellow equation. That's one answer, one solution to that yellow equation. There's one x value you should know right now that solves that yellow equation. Negative 2. That's what we just did, right? We just plugged negative 2 basically into that equation. And what did we get when we did all the number crunching? We got 0. It works. It satisfies the equation. Plug negative 2 in, the equation is solved. Again, we said there were 3 answers. We have one of them. It was just handed to us. All right, here's the work that we need to do. We need to find the other 2. So here's how. I'm going to rewrite this guy here. 2x cubed minus 3x squared minus 11x plus 6. What we were just handed was that negative 2 is a 0, right? Which means what is a factor? X plus 2, yeah? Anytime you got a 0, x minus that thing has to be a factor. So x plus 2, I've been writing it as x minus negative 2, but we can just put x plus 2 has to be a factor. The thing that's going to go in the parentheses, what's the highest power it's going to be? It's going to have? It's going to have an x squared, right? Because I know, like I'll put some plus signs in here, but I know when I distribute this x times this first thing, it better equal the 2x cubed, right? And so it's got to be an x squared thing to equal that 2x cubed. In fact, you could probably tell me. It's got, doesn't it have to be that to, like we're thinking about distributing and trying to build the original? Right? Because then this times this gives me 2x cubed. Great. Okay, let's try the next thing. The next thing I'm focused on is trying to build that minus 3x squared. Where am I going to get x squared terms? Let's see. There's this 2 times this 2x squared, right? Are there any other x squared terms? The second one, if it has an x, then this x times whatever I put there is also an x squared term, right? You could piece this together. You could just kind of solve the puzzle term by term. We're going to do it in a maybe a more efficient way. We're just going to do division. That's what we're after. Look, you know that x plus 2 goes evenly into that thing. So how many times does it go in? I don't know. I'm going to find it. I'm going to put it right here in the parentheses. So that's where division comes into this problem, right? The problem doesn't say divide, but we know we need to divide. We're trying to figure out how many times does x plus 2 go into that. So let's do our division. Okay, so what goes on the outside? X plus 2. And we're dividing that into this whole big thing with 4 terms in it. 2x cubed minus 3x squared plus 11x plus 6. I'm just going to use some of the same letters we saw before. Flip back real quick to the division algorithm. I think that's what it's called on the bottom of the previous page. Oh, minus 11. Thanks. Minus 11x. Okay, in the division algorithm, this was our f of x, right? The first thing. X plus 2. What is that called? That's the divisor there, d of x. This thing that we're looking for, we don't know it yet, but what is it called? That's the quotient, q of x. Isn't there something else after all that? Plus the remainder, right? Do we know what the remainder is? Feels like we don't know it, but we actually do. It's 0. 0. Because x plus 2 has to go evenly into that function, right? X plus 2 has to be a factor, meaning it's just x plus 2 times a whole bunch of stuff. We'll have more to say about that r of x being 0 soon. Okay, so let's see if we can fill in the long division here. What into what? X into 2x cubed, right? X into 2x cubed, x into 2x cubed, how many times? 2x squared, that's how many times? Put that above the x squared term, 2x squared. Okay, now we're distributing 2x squared times x plus 2. So we get 2x cubed plus what? 4x squared. What happens with the x cubes? They cancel, that's the goal. Negative 3x squared, so that's, it's not x squared?
No, negative is negative.
Right, it's negative. It's really easy to get distracted and think, oh, there's a subtraction up there. It's already a negative sign up there, but it's not x squared. It's negative 3x squared minus 4x squared. It's really minus 7x squared. Everybody see that? Okay, then we're bringing something down. Minus 11x comes down. And then we do x into negative 7x squared. X into negative 7x squared. How many times? Negative 7x. Negative 7x. Put it right above the 11x. And we distribute. Negative 7x times that x plus 2. Negative 7x squared. And then minus 14x. Lots of negative signs floating around. Really easy to get it wrong. Negative 25x. No, what is it? Positive 3x. Gotta really know your signs to do this long division thing. Yeah, so that's a positive 3x there. Then we bring down the 6. Okay, last one. X into 3x plus 3. Go ahead and distribute. And then act surprised when you see that remainder. But you need to work on your acting there. It's not convincing. What do we get when we distribute? 3x plus 6. And when we subtract? 0, my word. Didn't expect that at all. 0, it's the remainder. X plus 2 was a factor. See that? That was acting right there. Yeah. All right. So what does that mean? Let me try to clean up the mess I made in here. What goes in the parentheses? 2x squared minus 7x plus 3. We already had part of it before. We figured out the 2x squared, but then we sort of bailed on that process. But we had it right so far. Okay. So what does it mean? All right, well, I can clearly see x equals -2 is a solution. But we also need to make the other piece equal 0. 2x squared minus 7x plus 3 equals 0. What are our two main tools for solving that equation? Box method will factor if it factors. What's the other technique? Quadratic formula. Those are the two techniques. I actually think this guy does factor. Let's just get our answer up here real quick. 2x and x. I think it's a 3 here and a 1 here. You guys check. Do the FOIL. Tell me if that's right when you FOIL that out. Good. Okay, what value of x makes the second parentheses equal to 0? It's 3. First one? Yeah, but make sure you can see how to do that. A lot of folks just sort of memorize, oh, just change the sign. But that's no good if it's a 2x. So just solve the equations. It doesn't take long. X minus 3 equals 0. 2x minus 1 equals 0. And so then we just get our two answers. Add 1 and divide by 2. Add 3. And then we'll go ahead and list the other one that was given to us. What was it? -2 was the gift answer we were given. All right, I'm sorry, that went on so long. That was crazy. You're probably more sorry than I am that it went on that long. Any questions? That's more of a statement than a question. I agree. That was a lot. I wasn't prepared for it either. Yeah. Good. All right. Go through the activity. Let's see how far we can get. My answer?